All right. Well, thank you very much. Hopefully technology is supporting us and you guys can hear me, see my slides, and thank you for your time today. Thank you for the introduction. As was mentioned, my name is Jeff Butler. I sit as the principal engineer for transmission for Hubbell. In that role, I lead what I refer to as our technical compliance for transmission projects. And so part of that is overseeing insulators, polymer specifically, and the ability to meet customer requirements, specifications, and applications with this technology. So these are various slides that I'll be happy to share with the group after the presentation. They're very informative, and there's more here than I have the 40 minutes, I believe is the window of time that I've been given. So some of this I may kind of skip over or go through quickly, but I represent Hubbell Power Systems. We are primarily North American based manufacturer, but we have facilities in Asia, South America, and Europe, where we support the power utility industry as well as water, gas, other branches of Hubbell. So talking a little bit about the history of Hubbell, coincidentally, starting in the year 1888, Harvey Hubbell, began his company called Hubbell. At that time, another company not related to Hubbell called Ohio Brass also started. This company started out as a manufacturer of brass and bronze connectors, pieces, parts, also part of buckles and clips. And both companies separately at that time were very successful. The story of Ohio Brass continues in that they evolved into a company that also started manufacturing high voltage insulators. And the first cap and pin insulators chosen for high voltage transmission at that time, it was a 110 kV transmission line from the generation at Niagara Falls to Toronto in Canada. And that was built using Ohio Brass porcelain insulators. And actually, the original patent for the ball and socket insulator is an Ohio Brass patent for the same design that is used for porcelain and glass bells today. Moving on in the future, Ohio Brass also developed the first high voltage lab in the United States or in North America. And continuing in supporting of the industry, in about the years 1930, we began to see the introduction of glass as an acceptable material for high voltage insulators. So at that time, porcelain had been manufactured for a number of decades. Glass was introduced, but in the 1950s, we began to see non-ceramic materials developed and introduced into the industry. So in 1964 is when Ohio Brass took the initiative to begin research and development in non-ceramic or polymer insulator technology. This endeavor lasted 12 years, and in 1976, Ohio Brass launched its first generation of polymer insulators under the trade name of Highlight. And these were an ethylene propylene based rubber that's only to differentiate from the silicone rubber that is much more common today. But this ethyl-based rubber was introduced back in 1976 as this first generation. As further evolution of the industry, and these were at transmission voltages, so 70 kV and above. Distribution voltages began to adopt polymer insulators in the 70s, and then Ohio Brass, along with many other manufacturers, started developing silicone-based polymers in the 1990s. So silicone rubber for Ohio Brass was first introduced in 1996, and then the current generation of transmission insulators, what we refer to as the Quadrasil, that I will talk a little bit more about later, was introduced in 2007. So that is a brief history of Ohio Brass. And Ohio Brass was acquired in 1978 by Hubbell. So since 1978, Hubbell and Ohio Brass have worked together basically as the same company. So in that history, today we have capability and insulators installed throughout the world in voltages up to 1100 kV. That's 1000 kV AC, 1100 kV DC. These are in China. China is one of the few countries that has that high voltage. But over those decades, we have over 50 million polymer insulators installed around the world. Over 50 years of experience, as I mentioned, since 1976. Looking at line miles, over 300,000, and this is transmission lines, over 300,000 kilometers of transmission voltage lines, and well over 5 million transmission insulators installed around the world. So looking at our manufacturing footprint, as I mentioned, Hubbell as a company has a large focus in manufacturing in North America. So we have a facility in Aiken, South Carolina, and that's near where I reside, where we do polymer molding. Also, we pultrude our own fiberglass rod in that facility, and we also have design, manufacture, and testing, and then assembly of insulators. We're also supported by a facility in Mexico, which is primarily for distribution insulators, where we have molding and assembly. Similarly, we acquired a facility in Brazil that was previously known under the trade name of Balestro. We acquired them in 2023. They became part of the Hubbell family, so we now have a facility that supports Hubbell insulators in Brazil. And then we have two facilities in China. Not sure how well versed you are with the geography of China, but one is in the city of Wuhu, and the other is in the city of Rugao. And Wuhu is primarily for distribution insulators, and then Rugao has a broader range of transmission and distribution, as well as our silicone station posts are manufactured in the Rugao facility. So speaking a little bit of global manufacturing, let's look at some trends. So this was taken from a report that spanned from 2015 to 2025. Now here we are in 2026, so I could be due to update this information, but it is still relevant for our purposes. So at that time, they were looking at a trend from 2010 to 2015 of growth of insulator types. And at that time, polymer insulators in 2010 were 39% of the market, glass was 10.5, and porcelain was 50.5. And between 2010 to 2015, those changed to being polymer 40%, glass 11.8, and porcelain 48.2. So as you can see, porcelain is decreasing and polymer is increasing. At this rate, here in the next number of years, by 2030, we would expect that polymer insulators will surpass porcelain as the most common insulator material that is used throughout the world. And this is for new constructions, new insulators, new installations. And then that market growth during that time went from 4 billion to 5 billion, so a 22% market growth during that time from 2010 to 2015. And just as a point of reference, here in North America, that top line, since 1998, over 70% of new transmission lines in North America are installed using polymer insulators. So as far as in North America, that trend is much more accelerated in the use of polymer insulators across distribution and transmission voltages, and increasing into Hubbell recently supported a line, a 525 kV DC line that was polymer on the tangents, glass on the dead ends, but we're working on a 600 kV DC line that is going to be all polymer. So that just kind of speaks to the evolution of polymer insulators being accepted more broadly and at higher and higher voltages. So let's talk a little bit about polymer insulators just to make sure we're kind of on the same page. These are often referred to as composite insulators. Composite just refers to two materials that come together to differentiate those from ceramic insulators where you have a porcelain or a glass bell type. But the purpose of an insulator, no matter what the material is the same. So mechanically, they are to keep conductors up in the air, maintain clearances, maintain distances, hold lines where they're supposed to be. But the way that the insulators do that, whether it's polymer or composite or a ceramic, are a little bit different. So for a polymer insulator, the mechanical strength of the insulator is the fiberglass rod. So the most important part of the insulator is the fiberglass rod. It needs to be protected. It needs to maintain its strength, maintain its integrity, and then it is crimped to metal end fittings, which then help to transfer the strength of the fiberglass rod to the structure, to the tower, to the conductor, to the other parts and pieces. For a ceramic insulator, the mechanical load is carried by the compressive strength of the ceramic bell, or the porcelain or glass bell itself also serves to carry the mechanical strength as well as support the electrical function. So because of that, mechanically, there are different risks associated with the different components of a ceramic insulator or of a polymer or composite insulator. Now, both of these insulators live in an electrical world, so they have to function in an electrical environment. They have to be able to withstand the electrical stresses, the corona activity, electrical activity, leakage currents. So all of the electrical environment that goes with a high voltage installation, they need to survive that. all the while maintaining their mechanical strength and integrity. So when we're talking polymer insulators, talking composite insulators for Hubbell, there's actually two different types of materials that we use to achieve protecting the fiberglass rod. So the primary function of the polymer, as I mentioned, is to protect the fiberglass rod. So we can look at it as kind of a knight going into battle or a soldier going into battle. The arrows that could be attacking that soldier are the environment. It's the electrical activity, even mechanical stresses. So all those different activities that are occurring in the environment of an insulator are trying to destroy that insulator. So for Hubbell, we use two different types of polymers. So I have two shields represented there. The one in the middle of the screen I'm referring to as the Hubbell ESP. ESP is an acronym that Hubbell uses to define our distribution or our ethyl-based rubber. It stands for Enhanced Silicone Polymer, and it's an EPDM, or an ethylene propylene diene monomer, blended with a silicone rubber that creates a polymer alloy. And the primary defense mechanism for that material is tracking resistance. It is very tough. It is a durable material. So even if electrical activity is occurring on the surface of the rubber, it's going to be able to withstand that electrical activity for a long time, for a long duration. On the other hand, when we're looking at silicone rubber, or specifically Hubbell's silicone rubber, the primary defense mechanism of silicone rubber is hydrophobicity, or the ability for water to bead on the surface, so that you're cleaning contaminants, you're reducing leakage currents, you're reducing that electrical activity on the surface of the insulator. So while ESP is able to withstand that electrical activity, silicone rubber, while still durable, the primary function or primary mechanism that it protects itself is the hydrophobicity of the silicone rubber. But it is important to understand hydrophobicity is a characteristic of silicone that can decrease and increase and recover. And so we need to look at the life of the polymer even in those moments where the hydrophobicity may be lacking under high electrical stress. So when we're looking at polymer insulators, it is understood that there are challenges that are faced in the electrical environment. There's moisture, there's contamination, there's corona activity, electrical activity, which creates UV. There's also UV from the sun, from solar exposure. So all of that can lead to phenomenon of corona cutting, erosion of the polymer housing, and eventual failure mode is referred to as brittle fracture, or that's what the picture in the top corner, but the bottom left shows brittle fracture, where you see fiberglass strands that have been cut clean. It almost looks like they were cut with a knife, and then the remaining strands lack the mechanical strength in order to maintain the mechanical load. As I mentioned, the primary function of an insulator is carrying that mechanical load. So when insulators were first introduced, a lot of these stresses for the insulator were not well understood. So in the 1990s, an organization called EPRI, Electric Power Research Institute, based in the United States, as well as supported with STRI, S-T-R-I, the Swedish Technical Research Institute. They combined together to explore in the industry where there were some issues that were occurring with polymer insulators out in the field, where they were experiencing premature failure. In their investigation, what they found was the electrical activity was degrading the insulators primarily at the interface of the end fitting and the rod and the rubber. So where all three of those interfaces come together, as shown in the pictures there, that's where they were seeing the primary number of failures. Now, that's not to say that all polymer insulators were having issues, but those that were primarily were having it concentrated in this area. So that led them to understand certain aspects of the environment for the insulator that were not previously well understood. What that meant is it led to the focus of the performance of the insulator in those areas. So for Hubbell, we had good performance with our insulators previously because of the design, and I'll talk about that in a little bit later when I talk about our insulator design. But it did mean that there was an increased understanding in the industry of the effects of the electrical activity and corona for these polymer insulators. So that meant that there was an evolution in fiberglass rod, for example, where electrical grade was acceptable, but then everybody evolved into electrical grade corrosion resistant glass. It also led to the broader acceptance of a crimping technique referred to as circumferential crimping. And this was a crimping technology that Hubbell helped pioneer back in the 70s, but the industry became to widely accept that in the 90s. And today, almost every polymer insulator manufacturer is using circumferential crimping. And then it led to further advancement of materials, of polymer, of rod, of bonding, of molding of insulators. So it led to some greater focus on some of the challenges that these insulators face in order to extend the life of these insulators. One of those outcomes as well was the understanding of corona and corona activity, and that's referring to visual and audible corona. And so EPRI, together with STRI, provided a recommendation on a voltage gradient. So what I'm referring to here is that when a voltage level reaches a significant level on any object that's energized, it can reach a point where the air around the object begins to ionize, begins to break down. And that is understood through the manifestation of visual corona. And the picture in the top left, it is a black and white photo, so it's kind of hard to make out. But you're seeing those electrical discharges on the sheds of the insulator around the end fitting, and that is the manifestation of corona. It also emits a purplish bluish light, as well as an audible signature that sounds almost like cooking bacon or sizzling meat. So what was understood with further research from EPRI and STRI was that there were voltage gradients that perhaps were below what the threshold was for visual corona, what you would see out in the field on any given transmission line. And it was better understood that there were values below this that needed to be explored and understood. And this is done through simulation work in 3D modeling, coupled with laboratory testing. So basically that's a long way to say that the industry learned a lot following decades of experience in the field with polymer insulators, that some were performing successfully, some were not as successful, but it helped the industry as a whole understand better the designs, the performance, the application, how to provide proper shielding to these insulators, so that now we're able to better extend the life of these polymer insulators. So that's kind of a general level of polymer insulators. Now let's talk a little bit more specifically about Hubbell. So Hubbell, we took our polymer, we use our own proprietary silicone rubber polymer, as well as the ESP, the enhanced silicone polymer. Those are Hubbell recipes. They're controlled. Nobody else and no other manufacturers use those. So we took those and we compared them to other manufacturers, other materials that were available in the industry. And we learned where our rubber performed compared to other rubbers, other polymers, other composites that were available in the industry. And one of those things we learned was that we had superior UV performance. Now, I was talking about UV that comes from the sun, as well as UV that comes from the electrical activity of the corona discharge that I was just referring to. So the test that was performed here is often referred to as a QUV test, and it's performed in a chamber where you have 100% humidity, you have a period of exposure with a period of recovery, and it's similar to another test that's referred to as the DSET, or the Desert Sun Exposure Test. And that's the way that we can try and relate these hours of this test to real-world estimated lifespans. So we took plaques of rubber, put them inside this chamber, and tested them until we saw some sort of failure. And the failure criteria was cracking, checking, crazing of the surface, basically a breakdown of the polymer itself, extended loss of hydrophobicity, and then our threshold was a minimum of 8,000 hours. So we took our Hubbell silicone rubber, our Hubbell ESP, two other silicone rubbers, and two other liquid silicones, and we performed the test. Successfully, all of them did pass the 8,000 hour minimum, but you can see there that the Hubbell materials far exceeded the others. But the other interesting note was the difference between silicone rubber 1 and silicone rubber 2, which should have been similarly qualified, similar performance polymers, and yet we saw a dramatic difference in the performance of those two rubbers. So it just speaks to, even though a silicone rubber may be commercially available, may be manufactured by a given company, there could be dramatic differences in the performance of those materials, and that needs to be investigated. And then taking those times and estimating real-world exposure That's where the column on the right. But again, this does refer to just UV exposure. So this doesn't take into account a lot of the other environmental conditions, contamination, coastal environments, whether you're exposed to salt, perhaps industrial contaminants. So we're not saying that a Hubbell silicone rubber insulator should last 125 years. We're just saying that all other things put aside, UV exposure alone, that would be the estimated lifespan for the rubber. So furthermore, we looked at how to evaluate additional environmental conditions. So as I was just saying, that previous test was basically just a UV exposure. So IEC has a multi-stress test that was defined back in 2005 in the standard IEC 62217. It's located in Annex B, and it's referred to as the multi-stress test. And the multi-stress is that it controls temperature, humidity, rain, contamination, UV, and voltage exposure. So by almost simulating a small field environment, you're able to get a better understanding of the performance of the insulator as if it were out in the field. Similar failure criteria were evaluated for tracking for crazing with an erosion depth of 3 millimeters. So unlike the previous test where we did it on just plaques of rubber, this was done on actual sections of insulator. So you could evaluate the breakdown or the degradation of the rubber that could expose the fiberglass rod. And then the threshold was set for us to a minimum of 5,000 hours. The test per the standard does define 5,000 hours, but we actually increased that and ran the test for 8,000 hours. So the photos that are shown there are the insulators after 8,000 hours. So 60% more exposure in the test, and yet we still successfully passed the test. Now, unlike the UV test, we can equate this to real-world translation of a lifespan of the insulator, but it does represent that even after a significant amount of time to exposure to a very challenging environment, the insulator still performed very well. Oh, I clicked too fast. The other was we were looking at corona. So I referred to this corona phenomenon. So we took an electrode and you place it 1 millimeter from the surface of the rubber and you energize it at 12 kV. And you're basically forcing corona and high electrical stress right on the surface of the rubber. So in the multi-stress test, there was moisture, there was humidity, and so the silicone rubber with its hydrophobicity that I had discussed previously performed superior to the ESP. But in this particular test, where you're breaking down the hydrophobicity and there is no moisture present where the silicone rubber could demonstrate the characteristics of hydrophobicity, then you can see here in the table that the ESP material, the ethyl-based rubber, the ethyl and the silicone rubber alloy actually performs superior to the silicone rubber. So this speaks to what I was referring to of the durability of the ESP material to withstand electrical activity if it is present on its surface. This test, we take a piece of rubber, bend it over a grounded mandrel, just a steel metal piece. As I mentioned, put an electrode near the surface at 12 kV, and then we just energize it for a minimum of 1,000 hours, and you can see the range. Now, again, it was interesting to see the difference in the performance of what should have been similar materials. So here between silicone rubber 1 and 2, liquid silicone 1 and 2, there were dramatically different results in the behavior of the polymers. Now you may be saying, well, maybe there was a bad sample or it was mixed improperly, but this test was done with multiple plaques. 5 samples were taken, and so it was averaged across multiple samples of the rubber in order to determine these results. And then as the note at the bottom, that this test goes beyond just the hydrophobicity. So many times hydrophobicity becomes the key characteristic for silicone rubber that becomes the focus. But this demonstrates that hydrophobicity is only one aspect of silicone rubber that is important, but the durability of the rubber itself, the performance of the rubber itself is still very important beyond just the hydrophobicity. And then another test was adapted from a porcelain test, and this is very similar to the inclined plane test that is used today. I don't know if anyone might be familiar with the standard of IEC 60587, but this was an inclined plane test that was developed from the porcelain standard. So as I mentioned at the beginning in the history of Ohio brass, Originally, we were manufacturing porcelain insulators, so this was a test that we used to evaluate the integrity of the porcelain samples, and we adapted it for use for evaluating the integrity of polymer insulators. In that regard, porcelain, we had a minimum threshold for porcelain of 50,000 cycles. And now the cycles are, you're taking a plaque, you're placing it between two electrodes that are energized at 10 kV, 35 millimeters apart, and then you're cycling a conductive solution being sprayed on it every 90 seconds. And so that is a cycle. So you want it to at least pass 20,000 cycles. And you can see that for porcelain, 50,000 is the target, and the two Hubbell materials exceeded the porcelain. The silicone rubber too, as well, did exceed the porcelain minimum. And then you can see the ranges of the others. Again, very interesting to note the dramatic difference between the performance of what should have been similar materials with similar performance. So based on this testing, and this being now our fourth generation of polymer insulator, as I mentioned, with our first generation being released back in 1976, that has field experience up to and approaching 50 years, then for a recent project in the southwestern part of the United States, in the state of California, I provided a paper, and I can share that paper with you guys as well, that promotes or defends the evaluation of a 50-year life for Hubbell transmission insulators manufactured today, based on the testing that we have, the testing that we've performed, compared to the testing of the previous generations and the field experience that those have demonstrated. So the California ISO independent system operators, they agreed with that evaluation, and we were successful in winning that project because of the 50-year life evaluation that they were able to use for that project. So now let's talk a little bit about the benefits of polymer in general. So when we're looking at the use of polymer insulators versus ceramic insulators, porcelain or glass, I've alluded to it a little bit, but one of the key characteristics, as I mentioned, is that hydrophobicity, which is very effective in contaminated environments. So we saw a 70% reduction, or a 30% reduction, 70% better performance than ceramic insulators when it came to flashover voltages in a contaminated environment. There's also tremendous weight savings, up to 90% less than a porcelain or glass equivalent string, which is ideal for access and transportation, for handling. Typically, transmission line routes are in remote locations. Access can be challenging, so reducing weight, reducing transportation costs, reducing handling is very advantageous for many of these projects. I mentioned the hydrophobicity that is able to improve performance, especially in a country like Sri Lanka. There's an extensive coastline, being an island, so I imagine that there's a lot of salt spray, salt contamination, coastal environments where the hydrophobicity characteristic of silicone rubber would be advantageous. And then furthermore, in installation and construction costs, we've talked to contractors that can see a 50 to 70% reduction in the time needed to install polymer insulators as compared to ceramic equivalents. So let's go into a little bit more details of what I'm talking about. So this was the test or the study that we did where we were looking at contamination performance. So it may be a little challenging to make out this graph, but the line at the top is a new polymer insulator. The line in the middle is an aged polymer. That meant that we put it through an environmental chamber for the equivalent of 10 years of life. Put it through, I can't recall the exact hours, I think it was 500 hours in a salt fog chamber, but we basically wanted to demonstrate that even not new, a polymer insulator can still perform well, and that speaks to the hydrophobicity breakdown or the aging of the polymer. And then the bottom line is a porcelain bell string, and basically what we saw is across the full range of contamination, we saw superior flashover voltages on the polymer insulators than their porcelain equivalents. And these were equivalent leakage distances. So we matched the leakage distance of the ceramic string to the leakage distance of the polymer insulator, and we saw higher flashover voltages. Now, what does that mean? That means you're going to be able to get increased flashover protection, which in the event of an overvoltage or some kind of event on your line, you'll have greater protection, leading to fewer outages, which is then greater reliability for your line, which means it keeps the meters turning, the lights on, and end users happy. In addition to contamination performance, I mentioned a little bit of the coastal environment that is experienced in Sri Lanka. Also, this is a map that I was able to pull in regards to population density and some comments on air quality, or the effects of population density on air quality. So perhaps there are certain areas of Sri Lanka, and I apologize, I have not had the blessing of visiting Sri Lanka in person yet. Maybe that can be remedied in the near future. But as an island nation and with certain challenges environmentally, I imagine that contamination is a concern for certain projects. So in that regard, this is a table pulled from IEC 60815 in regard to the leakage distance ratios that would be recommended based on the pollution of the environment. And so that's where one advantage of polymer insulators is varying leakage distances based on the shed profiles. So there's multiple shed profiles that can be used within an insulator design for a polymer insulator and still maintain the same section length. Whereas when you're looking at ceramics, porcelain, or glass, many times you face the challenge of standard profile, fog type. There might be even an additional profile type, a desert type profile, the open flat profile, but there's limited options when it comes to increasing leakage distance without extending the length of your insulator string. I'll talk a little bit more about that in a couple slides. Another test that we did was in regards to power losses. So we looked at across a range of voltages what the power losses across an insulator were relative to ceramics, a porcelain string, and a polymer string. And this is important because what we found is that it's based on voltage and humidity. So the data is collected in the table in the middle, but it's kind of broken down on the right side. And this was taken with the assumption of an average home could be using 3,500 kilowatt hours per year of energy. And so based on that, if we were to use a 500 kV line at 30% humidity, you would be losing over 28 homes worth of power over 100,000 kilowatt hours. If it's 50% humidity, that's over 43 homes, 150,000 kilowatt hours. At 70% humidity, which looking at some of the environments there in Sri Lanka, it seems like there are some areas that may have high humidity, could be even year round, but certainly seasonally. So at 70% humidity, that's over 74 homes or 260,000 kilowatt hours. And at 90% humidity, over 100 homes, 114 and 400,000 kilowatt hours. So this speaks to the actual losses of energy that occur where that power is no longer going through a meter. It's no longer generating revenue. This is energy that is just lost to the environment just based on the selection of the insulator material, whether polymer or ceramic. So speaking in generalities a bit, the costs of cost benefit of polymer could be related to the material itself. In many cases, we're able to realize savings of providing a polymer equivalent insulator to ceramic for even a reduced price. This becomes more appealing as you go into higher voltages because the longer the string of porcelain or glass bells, then the greater the cost savings that could be realized for the polymer insulator. I mentioned a little bit about construction cost savings, but that is because you don't need to assemble anything. There's no insulator, glass or porcelain crates that need to be broken down, connected into longer strings. Polymer insulators come as a single piece. It's already assembled. You pull it out of the crate. It's ready to go. And then I mentioned the weight savings. So significant weight savings as well. And then operationally, there's cost savings because of the efficiency that you gain based on the contamination performance, based on reducing your leakage currents. So referring back to the Watts losses and the contamination performance that we just discussed. So Another aspect of polymer insulators that I was alluding to is because you can provide greater leakage distance over a given section length, you also have the opportunity to optimize a line design. So you're able to reduce perhaps the phase spacing or perhaps the tower height because you can target a specific length of a polymer insulator that gives you. I've talked a lot about our history, talked a lot about the importance of polymer insulators, the advantages of polymer insulators. So now let's talk about what Hubbell can provide. So we manufacture distribution, substation, transmission, voltage ratings from 10 kV, as I mentioned, up to 1100 kV AC and DC, different core diameters, 16 millimeters up to 40 millimeters for suspension, posts 24 to 90 millimeters. That's a full range of mechanical strength. Looking specifically at the distribution side, so lower than 70 kV, we have a few different product lines of a line post, what we call a PDI, a polymer dead end insulator, a Verilight suspension or VLS. That's what's shown on the far right. And those are direct glass bell equivalents. So those, we sell them in 3, 4, 5, and 6 bell equivalent sizes. So the idea being that you don't have to change your sag, you don't have to retension your line. You can directly replace glass bells with those insulators. And then we have porcelain pin types, as well as we are in development of polymer pin types. And that polymer is not silicone rubber or ESP, but that's a HDPE or high density polyethylene material. Targeting just a little bit, one of our unique designs for the VLLP or Verilight line post is a universal clamp. That's what's shown here in this image. This allows for the use of this product vertically or horizontally so that it will reduce your stock levels. You only need to keep one of these in stock because you can install it vertically or horizontally based on the desired application. When we're looking at transmission voltages, I went through a little bit of these sizes: suspension, line posts, and then a brace line post. But I also want to go into a little bit of detail on a brace line post or a BLP. And this is referred to sometimes as well as an insulated crossarm, but we differentiate that slightly in that an insulated crossarm is a multiple post or multiple suspension, similar to the image that is shown there kind of towards the middle of the slide. But a brace line post or insulated crossarm is effective in reducing, further optimizing your design, reducing your right-of-way, as you can see in the image on the right, where the line above used BLPs on the same tower, and the lower line has the wider right-of-way, the wider arms, so you're able to reduce that right-of-way. So we make a broad range of brace line post designs, so depending on your project needs. And then I'll kind of finish with these last couple slides of the quadricyl design. So I refer to this as our latest generation of polymer insulator. It refers to the redundant sealing system of the geometry of the end fitting and the rubber. So quad refers to similar to 4 redundant seals that are used, as well as a corona shielding ring, or this larger donut piece that is part of the metal end fitting. And as I mentioned, Hubbell had success in the performance of our insulators even in the 70s and 80s because we've always had a design that includes this corona shielding ring. So this larger ring helps to distribute those electrical stresses right at that interface of the end fitting and the rubber where it all comes together. So having that piece on our initial designs, even back in the 70s and 80s, helped improve the performance of our insulators. We maintain that design even today as having the largest corona shielding ring integral or as part of our end fitting of any manufacturer on the market today. Another aspect of polymer insulators that sometimes presents a challenge is live line testing. So this is a polymer insulator tester that Hubbell manufactures in support from EPRI, Electric Power Research Institute, that same company that did research back in the 90s on polymer insulators. They developed this product, and we are the manufacturers and commercial arm for marketing and selling this product. And then kind of the last highlight of Hubbell capabilities is our high voltage test labs. We have multiple labs that we use in North America for high voltage testing. You can see the list of them there. They're ISO accredited, which is the same as other global labs. I mentioned STRI, other large organizations such as KEMA or CHESI that have accredited high voltage labs. We are ISO certified for quality, safety, and environmental. And then just kind of in summary, there's multiple advantages to using polymer insulators. I've demonstrated some of the advantages of Hubbell polymer insulators in the performance of the products and the durability of those insulators and lasting an estimated life up to 50 years. Hubbell is an ISO certified, supported with ISO accredited labs. We're involved in the industry. I'm part of IEC, part of CGRE. Not sure if anybody from this group is going to the Paris session for CGRE here in August. But if you're there, I look forward to meeting you and chatting with you more about the exciting challenges that you're facing there in Sri Lanka. But I guess in conclusion, as I mentioned, I'll share these slides with you, and you will be able to enjoy them. But I appreciate your time. Thank you very much.